I'm going to tell you about a project I've been working on for the past maybe 3 or 4 years. So this is going to be about 2 systems of electroconvection in fluids. But before that, I also are going to tell you, or just a little bit about also recent work on SQG, which is quite related to the electroconvection. Okay, so non-locality in fluid models comes in different ways. The incompressible Navier-Stokes equations and Euler equations are non-local via the pressure. By contrast, other models are non-local because the fluid velocity and the dissipation can be given in terms of non-local expressions. So here are some examples of transport and non-local diffusion equations. The first example is related to the electroconvection system that I'll talk about later on. Here we have the incompressible Navier-Stokes equations coupled to an active scalar equation. We have a critical dissipation lambda, which is square root of Dirichlet Laplacian. Another prototypical example of a non-local equation is, for instance, the critical SQG, which again has the critical dissipation lambda, and the drift velocity u is related to theta via a Riesz transform. Another example that I will also address later on is given by an electroconvection in porous media model. So here we have non-locality coming from the dissipation, and the velocity u is related to the scalar, which in this equation is rho, via a nonlinear expression. So here we have something that looks like quadratic in rho, and it's doubly non-local due to the Riesz transform and the Leray projection applied to it. So a little bit more about the prototypical example. So this is the case of inviscid SQG in the whole space, which is a nonlinear, non-local equation for the scalar theta. So here the fluid velocity is related to theta in terms of Riesz transform, which in the case of the whole space is given with an explicit kernel. And our perp is just rotation by 90 degrees. Because of this relation, also one can see that the velocity is divergence free. The dissipative SQG have an additional term. They have a dissipation of order S. So here again, because we're in the whole space, the fractional Laplacian has a formula with explicit kernel. And we can look at the scaling of this equation. So if theta satisfies the equation, then also lambda, theta sum lambda will satisfy the equation. In the case when S is strictly greater than 1, then we have that the dissipation beats the nonlinearity. So the nonlinearity looks like quadratic in theta, and it involves one derivative of theta. So if S is strictly greater than 1, we have the dissipation beats the nonlinearity, and then the global regularity is known. In the case of S equals 1, the equations are called critical SQG. So in this case, we can see by scaling that theta lambda satisfies the hyperbolic scalings, and that the L infinity norm is critical for the equations. Also, one can show that the L infinity norm is the smallest, actually. So L infinity norm is conserved in time. So basically, the L infinity norm of theta is bounded by the L infinity norm of the initial data. And if we take initial data that is small in L infinity, the global well-posedness is known for more than 20 years. In the case of large data, there are by now many proofs. So there are the proofs by Caffarelli Vassor, which were based on the Georgi technique of zooming in. There is a proof by Kiselev, Nazarov, Boberg, based on the invariant models of continuity. And the last two proofs, which were based on the nonlinear maximum principle, for which I'll tell you a little more in a second. The case when S is strictly less than 1 is called supercritical. In this case, the nonlinearity beats the dissipation. And in this case, the global regularity is open. And so it is in the case when S equals 0, when we consider the implicit equation I didn't say on the previous slide, but the implicit SQG also has open global regularity. A little more about the idea. So this is what will be an idea for global regularity in the case of critical SQG in the whole space. So we would like to estimate the magnitude of the gradient of theta, or in this case, I've written grad perp theta. So we start by taking grad perp of the equations, and we obtain a very nice linear transport and local diffusion operator on the left-hand side. And however, on the right-hand side, we have the term, the so-called stretching term, which is quadratic. Then if we consider the scalar equation for the grad perp theta squared, again, we can write it in a form so that it has the good transport and non-local diffusion part. And then we can actually get this good dissipation. And from the stretching term, we are going to obtain the cubic term after multiplying by grad perp theta, which can be bounded by the gradient of the velocity q squared. So if we think of Riesz transforms, we can say that if u is basically like theta, then gradient u must be like gradient theta, which we call q here. So it comes that the bad term on the right-hand side is cubic. Now, looking more careful, we can see that this dissipation that I wrote is precisely equal to that quadratic expression here, for which we use a crucial nonlinear lower bound, which was established by Konstantin Vikl. So basically, this quadratic expression is bounded from below by a cubic quantity q cube with some prefactor. Now, in the case when we have that the L infinity norm of theta is bounded by the L infinity norm of the initial data, and in the case when the initial data is small in L infinity, we can think that this is enough to use to absorb the cubic term on the right-hand side using this dissipation. And this is more or less the idea of Konstantin Wu in the result for small data. However, if you have large data, this, of course, is not enough. You basically need to rely on Hörder estimates first. Instead of trying to obtain bounds for W1 infinity norm of theta, you need to first get Hörder estimates, and after that get bounds for the gradient. And also there is the little additional problem that gradient u is not exactly like grad theta, because this is not Burger's equation. But again, one can do the estimates and obtain the global regularity. So one other thing that I would like to mention is that in the case of the whole space, once you get your solution to be Hölder continuous, then the problem becomes subcritical in a sense, and one can obtain that the solutions are actually smooth. This is, of course, not the case if we consider the critical SQG in bounded domains, where the problem for global regularity is a hard open problem. But in the case of bounded domains, what we know is that there are global bounds, global interior Lipschitz bounds, and also there are global Hölder bounds up to the boundary. So these are the two more recent results on this subject. Now, in the case of bounded domain, additionally to what I said for the whole space, there are a few more challenges. For instance, all the non-local operators do not have explicit kernels, so that's one. And also, there is no translation invariance. So once you try to take derivative or finite difference of the equation, you need to deal with commutators. But the strategy of the proof is along the lines. So first one obtains L infinity bounds. So the L infinity norm of theta bounded by the L infinity norm of the initial data. Then we do interior Hölder estimates with exponent lambda, with exponent alpha. And after that, once we establish the Hölder bounds, we do the global interior gradient bounds. So in this talk, I will continue talking about electroconvection models. So I will introduce the models, and I will discuss their global regularity when available and their long time behavior. So first, we consider an electric field, which I call here E, which satisfies the Maxwell equations for electrostatics. Namely, we have that the three-dimensional divergence of E equals rho, which is the charge density, and the curl of E is equal to 0, which means that we don't take magnetic effects into account. We consider a particular case when the charge density is confined to a two-dimensional region omega. So this is motivated by a work of group of physicists. This is the group of Morris, and I'll give you on the next slide schematic of their experiment. So we'll think of rho as given in terms of Dirac delta measure on omega. So it will be a surface charge density Q times the Dirac delta of omega. And we have that the surface charge density is carried by two components, one due by the fluid velocity, and a second component due to the parallel component of the electric field. So this E parallel is the parallel component of electric field to the two-dimensional domain omega. The fluid is also confined to the domain omega and satisfies the incompressible Navier-Stokes equations, which are forced by electric force and body forces. So here is the schematic. We have a nearly two-dimensional fluid, smectic fluid or soapy fluid, which here is represented by this annular domain omega. So this fluid is suspended by the two electrodes, which here are denoted by K sub 1 and K sub 2. And the two electrodes are kept at different voltages, which is used to drive a current. So the authors or the group makes a relations between what they see with the fluid starts exhibiting very complex behavior, and they compare it with the Rayleigh-Bernard convection. So we keep the boundaries, the two boundaries of omega at different voltages, which I denote by V and 0. Then the electric field E is expressed via a potential phi on the cylindrical domain Q with base omega. And using that, we have that the curl of E is equal to 0. We obtain, so using that the curl of E is equal to 0 and the divergence of E is equal to rho, we obtain that the potential phi has to satisfy the Poisson equation. So we have the three-dimensional Laplacian of phi is equal to what we call rho. But in this case, we have something that is singular that looks like the Dirac delta of omega, so which gives a two-dimensionality, which we consider in this case. And we have non-homogeneous boundary conditions. So of course, we can solve this Poisson equation using the superposition principle. We obtain that the solution is equal to a harmonic function, plus this is what we obtain for the non-homogeneous problem with 0 boundary conditions. And this is a natural way of the appearance of the non-local operator lambda. One can see that the parallel component of E has last component is equal 0. And when you take divergence of it, you obtain the Laplacian of that harmonic function, so something very smooth, plus lambda Q. So going back to the equations, we can rewrite them in the following form. So we have now the Navier-Stokes equations, and from the electric force, we have these two terms. One of them looks like Q retransform Q, and the other one looks like Q retransform that capital Q. So this capital Q was the one that is basically a very nice smooth quantity, and we treat it as a given forcing, and it depends entirely on the applied voltage at the boundary. And for the Q equation, we obtain the non-local dissipation, lambda Q. And on the right-hand side, again, we treat the lambda Q as a forcing, as a given nice forcing. So I'm going to discuss briefly the global regularity of the system, which we obtained earlier with Constantino, Genti, and Vico, and then I'll tell you more about the long-time behavior of the solutions. So first about the global regularity, starting from sufficiently smooth initial data and having the two forcings sufficiently regular, there exist unique smooth solutions, U and Q, for all time. So the result holds in the case of bounded domain and also in the case of periodic boundary conditions. However, due to the use of nonlinear maximal principle, one can see that the solutions behave in a quite bad way in terms of the initial data. So they depend in a doubly exponential way. And this is not going to be good for us later on when we want to study the long-time behavior of the solutions. We would like to obtain some bounds which forget the initial data. A little bit about the construction of solutions. The construction of solutions is done in 2 steps. We are going to use Gaulian approximations both for the fluid velocity U and for Q. The ones for the fluid velocity are based on eigenfunctions of the Stokes operator. The one for the Q equation for the Q are based on the eigenfunction eigenfunctions of the negative Laplacian. So the first approximation is to look at the following system of nonlinear ODEs. So for both Q sub n, the approximation Q sub n and U sub m, we have classically that the fluid nonlinearity cancels out when we multiply the equation by U sub m, and also when we multiply the equation for Q by lambda inverse Q, there is also cancellation of the nonlinearity for the Q equation with the nonlinearity on the right-hand side of the U sub m equation. So this is crucial on that level. So this basically leads to some lower order norms remaining bounded for all time and gives the global existence of solutions. If we want to obtain a better regularity for these solutions, if we want strong bounds, then we need to take derivatives of the equation, and for this we use the following commutator estimate. So here V in 2 dimensions will belong to the space W2P, namely 2 derivatives in LP, and V is going to be tangent to the boundary. So it will satisfy that property that the fluid velocity satisfies. And then if we consider this vecting, so if we consider this commutator between this first derivative and a first derivative, but which is non-local in this case given by lambda, we know that the commutator estimate should gain 1 derivative. So if I have 1/2 derivative plus 1 derivative, there should be 3/2 derivatives falling on F. But for this estimate to work, we really need the vector field V here to be having regularity of W2P. So W1 infinity does not suffice, something that will be enough if instead of lambda we had a gradient. So in a sense, commutator estimates are expensive. So using this kind of commutator estimate, we can take now derivatives of the equation and we obtain a bound for the norm of Q sub n, which depends, which is uniform with respect to the initial with respect of the initial data, but however it depends on U sub m. However, this is enough. If you fix m, you can pass to the limit, and you can arrive to the second so-called good approximation, where we have PDE, which has a nice structure of transport and non-local diffusion, and then coupled to the Galerkin system of nonlinear ODEs. So for this system, now we can do LP bounds, so we can obtain that the LP norm of Q is uniformly bounded and independent of the drift U sub m. Then using that the right-hand side, now if I take P equals 4, the right-hand side looks like I have a forcing for the Navier-Stokes in L2, and the regularity for Navier-Stokes with L2 forcing is well known. So then I obtain more regularity for U sub m in these classical spaces, which I can use and get more regularity for the Q equation, and going back to U, and at the U equation, more regularity for the U equation, and then passing to the limit does the job for constructing the solutions. The uniqueness can be obtained in the space for strong solutions. So basically, these are the classical spaces L infinity the domain of A 1/2, L2 domain of A, and same kind of regularity for Q. So one just considers differences of solutions. So U and Q are the difference of two solutions, and the bar variables are their semi-sums. And one can write the system for the differences, and again use the crucial cancellation of two of the nonlinear terms, and just do L2 estimates to conclude the uniqueness. In the case of periodic, on the torus, in the case of periodic domain, one can show much stronger result. So we can prove uniqueness only if you know that the fluid velocity is L2 in the domain of A, which is, more or less what we have above. But for the Q, we have much less. We have that Q is L4 in time, L4 in space. So this stronger result is based on a commutator estimate. So this estimate is valid for powers of the square root of the Laplacian, which can be even negative. And it allows us to transfer alpha derivatives between the fluid velocity and F. So here the bracket norm is a stronger norm than 1 minus alpha derivatives of U being in L infinity. And using this commutator estimate, one can bound this second nonlinear term in the Q equation, in the following way. And one can obtain uniqueness because now I have this nice or the inequality where the right-hand side is integrable if Q is L4, L4, and the velocity is in L2 in time domain of A in space. Okay, so this basically gives the uniqueness. Now, regarding the long time behavior, so I would like to show how one can obtain bounds which forget the dependence on the initial data. So here are the ingredients. We're going to rely on the following generalized Córdoba-Córdoba inequality, which I have stated here in the case of bounded domains. So we think of the function phi as which can be in general C2 convex function such that phi of 0 is equal to 0. In our case, we will always apply this with a phi which is an even power. So for us, phi of f will be f to the power p. So the left-hand side of this estimate, so this is a pointwise lower bound, the left-hand side has a prefactor, a constant over the distance of x to the boundary to the power s. And then it has this term, which in the case, when I take phi to be f to the p, gives me the nice expression on the right-hand side, is gives me f to the power p. So this is basically used to obtain that the LP norm of the solution is bounded by the LP norm of the solution at initial time. So if I take that pointwise bound and if I integrate, and if I do that over the periodic torus, I can obtain the nonlinear fractional Poincaré inequality. For this, of course, I'll need Q to be mean 0. So the integral of Q over the torus to be equal to 0. And then I'll obtain a similar expression as I showed you before, but this time the integral of this nonlinear term is bounded by the LP norm of Q to the power P plus some nice damping term. So this kind of estimates, of course, work only either on the torus or if you are in bounded domain. They are not valid for the whole space. So from now on, I will consider the case of the periodic torus. And of course, I would like all my quantities to be mean-free. There is one little difficulty in the case of periodic domain, that if you consider the fluid equation, one of the terms on the right-hand side do not integrate to zero. To deal with this obstacle, we perform a change of variable. We write u as the mean velocity of u plus mean free velocity. And then we change the variable. We translate the spatial variable with a time-dependent displacement, which look like a time integral of the mean velocity. And doing that, we arrive at a system which now has both u and q with mean 0. And the solutions to this new system are in one-to-one correspondence to the solutions of the old system. Now, the second ingredient will be a uniform Gronwall lemma. If we consider a norm y, which satisfies an ODE like this, with the right-hand side a constant f and a function f depending on time, which obeys the following time average bound. So the integral in time, so in an interval of length 1, is bounded by some constant, an exponentially decaying factor, plus another positive constant. Then the norm y satisfies the pointwise bound. So here it is important to mention that y0, which is the initial data, and g0, which comes from the right-hand side, will be basically the terms. So these two quantities will involve norms that depend on the initial data. And it is very important that every time when we obtain them, they come with exponentially decaying factors. And the rest of the terms will be harmless, so they will be easy to deal with. Okay, so here is the strategy. So we will have three norms. So N0 on the right-hand side will be the so the weaker norm. So this will usually come from our previous step, and we'll be able, we will know that the time average, local time average is bounded with the same quantity as we had in the Gronwall lemma, an exponentially decaying factor plus something that involves only forcing terms. Then we'll have a stronger norm n sub 1, which we would like to estimate, and yet one even stronger norm than n sub 1, which obeys this kind of inequality. So then using the exponential Gronwall lemma, we are able to obtain from knowing that the right-hand side has time average bounded as such, so it obeys this A estimate, we obtain a pointwise estimate for the norm n sub 1. And after integrating this inequality, we are able also to obtain immediately an estimate of type A for n sub 2. And this will be basically the idea to progress and get better, stronger norms with decaying factors in front of terms that involve initial data. So I'm not going to go in details. So one first does the LP bounds for the Q equation. So here for every if you take the Q equation and if you multiply by Q to the P minus 1, one obtains this inequality, which gives a pointwise bound for Q. And here notice that I already have used one of the terms in the nonlinear Poincaré inequality. The other nice damping term I use only in the case when p is equal to 2 to obtain that this norm satisfies an A-type bound. And then we look at the first level of energy, where we use the crucial cancellation on this level, and we obtain a P-type bound for the lower norms for U and Q, and also by integrating, of course, a bound of type A for this norm of U. And then we go second, third, fourth, and fifth energy in a similar manner using our strategy. And we end up with bounds for U and Q in very strong norms. So if we consider the evolution of U and Q in the phase space V, so here V is the domain of A1/2 L4 for Q. So that was the space for which we show that the solutions are unique in the case of periodic domain. We have that the solutions are given in terms of a semigroup, which are denoted by S. And we obtain the existence of absorbing bow, namely for any initial data in the phase space V, we can find time which depends only on the norm of U and Q in V, such that for any later time than T0, the solution enters the absorbing bow. And once again, so here we have these very strong norms for U and Q, which are obtained after going through the 5 energy levels, which I skipped. Okay, then we can show continuity properties of the semigroup. Actually, we have the semigroup is Lipschitz continuous from the space H. So here H is just the usual H space for the fluid equation and L2 for Q. From H to H, from the phase space V to V, and from H to V with the usual singularity at time t equals 0. Then we also have we have injectivity of the semigroup, namely we have backward uniqueness. If you have 2 initial data in V, and if the solutions coincide at time t, they must be the same initially. This has a very nice proof which works for many other equations, but because of lack of time, I'm going to skip the proof of the uniqueness for the semigroup. So having the compact absorbing bow and the continuity properties and injectivity, one arrives at the global attractor. So one obtains that the system has a global attractor, which is a compact set in V that is invariant under the evolution, and it's the largest such set, and all the solutions starting with initial data in V converge to that set, and the set is connected. We have that the global attractor has finite fractal dimension, namely this dimension is bounded by a quantity that depends only on the norms of the forcing terms. And in the case when we have that the body force is 0, so in the absence of body force, one can also see that the attractor is just a singleton, namely it is given by fluid velocity equal to 0 and Q equals to that quantity capital Q, which is a known quantity. Now, for the last few minutes, I would like to tell you about the second harder electroconvection model. So in this case, we have the active scalar equation, which I have written here for rho, which is affected by the fluid with critical dissipation. And we have that the fluid is incompressible and is forced by electrical force, which is similar as before. It is given in terms of rho risk transform rho. If we replace the Navier-Stokes equations by Darcy's law, namely, if we have the following balance, so we have that U plus grad pressure is equal to the force, then using the incompressibility, we obtain that U is given in terms of rho via the Leray projection rho risk transform rho. So here immediately you see that in contrast with the Stokes operator, in which we have negative Laplace U plus gradient pressure, we lose two spatial derivatives. So of course, these equations are more singular. So for this equation, with U expressed by rho in terms of doubly non-local nonlinear expression, we have that the global regularity is an open problem, which seems to be very challenging. What we were able to prove with my graduate student Eli Abdo is that if we have existence of weak solutions, if we start with initial data slightly larger than L2, then if we have initial data in LP, the LP norm remains bounded in terms of the initial data. And then also the local existence and uniqueness of strong solutions. So these are under the lines of what is known for SQG. Now, regarding global regularity, if we have small initial data in a space slightly smaller than L infinity, so then we have that the solutions are globally regular and they are actually analytic. Similarly, as for SQG, once we have Hölder continuity for rho, then we have that the solutions are actually smooth. So this is a sufficient condition, even when we have large initial data. And also it is known, we were able to prove that for subcritical equations, when we have lambda to a power between 1 and 2, then we have global smooth solutions for arbitrary data. So here is the most important theorem. So once again, something that is known for SQG, if you have small initial data in L infinity, you know, for SQG, the solutions become smooth. This is open in the case of the electroconvection in porous media. But our result is if we start with initial data in a Bezo space with the same scaling as L infinity, and if we have small data in this space, then the solutions are analytic. And I'm going to stop here. Thank you very much.